Hello and welcome to this lecture on advanced electric drives. In the last lecture we are discussing about the vector control of permanent magnet synchronous motor or PMSM drive. By vector control we mean we should be able to control a permanent magnet just like a DC motor. In other words, we should be able to control the torque component of current and the flux component of current independently. Let us take again a look at the phasor diagram of permanent magnet synchronous motor. So, we have the permanent magnet rotor which is shown by a field winding and this is the corresponding current and the current is IFR, the rotor field current. And then we have the induced EMF because of the field winding flux, that is IFR, and this is EF. The stator current can be in any arbitrary direction. So, we can draw the stator current like this. This is IS, and we can say this is the D axis. This axis is called the D axis, the direct axis, and this axis is the Q axis or the quadrature axis. The stator current IS can be decomposed into two components, one along the D axis and the other one is along the Q axis. The component along the D axis will be in line with the flux, the rotor flux. The component in Q axis will be quadrature to the flux. Now, we can resolve this into two different components like this. If we project on the Q axis, this component will be known as IQS, the Q axis stator current, and if you project this IS along the D axis, we call this current to be IDS. So, we have two currents, IDS and IQS. We can name them in a little different way. We can call IDS as IF, the flux component of current, because we can see that IDS is in phase with IFR. IFR is the rotor equivalent current. Rotor is actually a permanent magnet. We do not have any field winding in the rotor, but however, IFR represent the effective rotor current due to the permanent magnet. It is a hypothetical current IFR. So, IDS is along IFR and we will call that current to be IF. So, this is the flux component of current, we can call this to be IF. And similarly, IQS is along the Q axis, we will call this component of current to be IT, the torque component of current. So, in permanent magnet synchronous machine, we have no freedom to vary the rotor flux. The rotor flux is constant because the rotor is excited by a permanent magnet. However, we can control the flux from the stator side by controlling IDS. So, we are seeing a block diagram of this control in the last lecture. This block diagram is as follows. This is a closed loop block diagram of a vector controlled permanent magnet synchronous motor drive, and we have two components of current that I was discussing, that the flux component of current is IF, it is produced from the stator side. The torque component of the stator current is IT, and this IF and IT are in the rotor reference frame. Now, what do we mean by rotor reference frame? We are taking a reference frame attached to the rotor. The rotor is rotating at rotor speed. Now, if we see here, this is the rotor, and rotor is moving away. This is the physical phase A axis. We have the actual windings of the motors are like this. This could be phase A and phase B could be shifted from this by 120, and phase C is shifted from this by again by 120. So, this is phase A, this winding is phase B, and this winding is phase C, and this rotor is rotating at a speed that is equal to omega r. Omega r is the rotor electrical speed. Now, if we see the angle between phase A and the d axis, this angle is theta r, the rotor angle. And again we have already defined the angle between IF and IS. This angle is delta prime, which is something like torque angle, and we have already shown that the torque is a function of delta prime. So, in this situation, the reference frame is attached to the rotor. So, we have already derived the equations for the d axis and q axis. The d axis stator winding is housed here. So, this we can call to be ds, the stator winding in the d axis, and this winding is the qs, the stator winding in the q axis. So, this reference frame, the dq reference frame, is attached to the rotor, and this IT and IF are the currents in the rotor reference frame. So, we need to transform IT and IF into physical IA, IB and IC, and physical IA, IB and IC are the currents in the three phase stator windings. So, in this case we have phase A, we can call this current to be IAS, phase B, this current is IBS, and phase C, this current is ICS. So, what we need to do, we need to transform IT and IF, these two currents, this is IT is the torque component of current and IF is the flux component of current, into IAS, IBS and ICS, and for this we need a transformation. The transformation will involve theta r, because this frame, the reference frame is rotating at omega r, theta r is the angle here. So, when we transform this IF and IT into IA, IB and IC, we need the angle theta r. So, theta r will be fed here. This will require theta r. Theta r is already here. So, in this case we need this theta r. This theta r will transform this into the stator currents, and the stator currents are IAS, IBS and ICS. In fact, we do this in two stages. First of all, we have two orthogonal components. IT and IF are mutually orthogonal to each other. IT is in the q axis, IF is in the d axis. So, we convert these orthogonal components in the rectangular coordinate into polar coordinate. So, this IF and IT are transformed into IS and delta prime. So, we will be transforming this IF and IT into IS. IS is this current, the stator current, and then delta prime is the angle between the d axis and the current vector, that is IS. So, how do we calculate delta prime? Delta prime is calculated once we know what is IT and what is IF. We can calculate delta prime as tan inverse of IT by IF, that is the delta prime, and we also need the magnitude of IS. IS is the stator current which has got two components, and the components are IF and IT, and their orthogonal component. So, as per the Pythagoras theorem, we can say that IS equal to IF square plus IT square under root. So, this IS is known and delta prime is known, but we need to transform this IS into IA, IB and IC. So, what we need is the rotor angle theta r. So, this theta r is added here. So, the total angle is theta s, and theta s is this angle. Theta r is the rotor angle plus delta prime. So, the current vector I s is shifted from phase A by an angle theta r plus delta prime, and with this angle what we do here, we transform this into IAS, IBS and ICS, and then we can have inverter with current control. We compare the reference current, these stars are actually the reference current, IAS star, IBS star and ICS star are the three reference currents of the respective phases. They are compared with the actual currents, and the actual currents are obtained by Hall sensors. So, these are the actual currents IAS, IBS and ICS. They are obtained by having Hall sensors in the three phases of the stator of the PMSM drive. So, we sense IAS, IBS and ICS, and these are used for feedback purpose. So, we feedback these actual currents IAS, IBS and ICS, and we get an error. There is a comparator, and we have an error in the output, and this error is fed to a hysteresis controller. So, we have a hysteresis controller here. This is the hysteresis current control. So, we have hysteresis controller here, which will trigger or generate the gate drive signals for the inverter. Inverter here is a 3-phase inverter having 6 IGBTs or 6 transistors, and this inverter is feeding the 3 phases of the PMSM drive, and the hysteresis controller will be generating the gate drive signals of this inverter, and the inverter will be driving the current into the stator of the permanent magnet synchronous motor for the control. Now, we also need the position. The position information, that is theta r, is obtained by a position encoder. We have a position encoder here which is mounted on the rotor shaft. We have the rotor shaft in this case. The encoder is mounted on the rotor shaft, and this gives us the mechanical position of the rotor, that is theta r m. The mechanical position is multiplied by the pole pair, that is p by 2, to generate the electrical rotor position, that is theta r. In the model, we have the electrical rotor angle theta r, and the theta r is used for transformation into IAS, IBS and ICS, and hence for transforming this into 3-phase current, we need the electrical angle theta r, and this is added with delta prime to give us theta s for the reference current generation. As we already seen that the flux controller, flux will remain constant up to the base speed, and after the base speed we go for the flux weakening. So, this function generator generates constant flux up to the base speed, and after the base speed we go for the flux weakening. It means after the base speed the voltage is maintained constant, and then that is achieved by reducing the flux. How can we reduce the flux? Because the rotor flux is constant. The rotor flux is in fact given by a permanent magnet. So, we cannot change the field current like a wound field synchronous machine. But in this case the flux is reduced by injecting a negative IDS. How is a negative IDS injected? We can show that in this phasor diagram. So, here we can see that IDS is helping the rotor flux, that is IFR. IDS and IFR are in the same direction. Now, if we take a situation where we have the field here, the field current here, IFR, and we need to go for flux weakening. For flux weakening, the resultant flux has to be reduced. So, what we do here, this is our d axis, this is the q axis. We inject Is in such a phase angle, this phase angle is delta prime, that IDS is negative. IDS is in phase opposition with IFR. Again here Is can be decomposed into two components. One is IQS, this is IQS, the q axis component of the stator current, and then this component is IDS, the d axis component of the stator current. Now we can see here that IDS is opposing IFR. So when IDS is opposing IFR, the flux is reduced, and the resultant of IF and IS is going to be low. So if we find out the resultant here also, we can do that by completing this parallelogram. This is the resultant of IS and IFR, and we call that to be Im is the magnetizing current, Im, that will be reduced because of negative IDS, and that what happens in flux weakening. In fact, in flux weakening, delta prime will be higher than 90. So if this angle delta prime is higher than 90, we can go for flux weakening. So we can say that for flux weakening, delta prime should be more than pi by 2. So we operate at constant flux up to the base speed, and beyond the base speed we go for the flux weakening, and that is achieved by having a negative IDS. So this is a closed loop control block diagram of the vector control permanent magnet synchronous motor drive, and this drive is quite popular, and the application of this drive are in automotives, also in high performance applications. So wherever we need to have high performance application with compact size, we go for PMSM drive. So the applications here automotive applications, in that case we go for PMSM drive, where the size of the motor is small, it is compact, but the power is quite substantial. Sometimes it is also used for traction application. Traction is also automotive, but at little higher power. It means beyond 100 kilowatt to 1 megawatt we can go for this kind of motor. And then in high performance application, in medium power range, this means we can go from something like 10 kilowatt to about 500 kilowatt without much problem. So this is the application of permanent magnet synchronous motor drive, in which the MMF is distributed in the space, the induced EMF is sinusoidal, and the torque ripple is also reduced because the induced EMF is sinusoidal. We inject the motor with sinusoidal current and voltages, average of the current and voltages are sinusoidal, and hence this drive is suited for high performance application. We will see a new class of motor. We have already talked about the permanent magnet synchronous motors, which are used for those applications where the space is a constraint, something like space application. The weight is a constraint. So the permanent magnet synchronous motors are used for those applications where the torque to weight ratio needs to be high. We need high torque, but the weight should be minimal. We have another class of motors which can also be used for lightweight applications, and those motors are called the switched reluctance motors. So, now we will be discussing on switched reluctance motor. In switched reluctance motor, the torque is produced by the variation of reluctance or permeance of air cap. In general, we see that whenever we have an inductor, the stored energy is half into Li square. So, we can say that E is equal to the stored energy is half Li square. This is the stored energy in an inductor. Stored energy in an inductor or in a coil. So, if we want to find out the torque is the derivative of this energy with respect to the position. So, if there is a variation of the energy with position, we will get a torque. So, if we differentiate this dE by d theta, we get the torque, and that is equal to d by d theta of half Li square. Now, usually the current is an independent variable. It is injected by an inverter or a converter. So, I in this case is not dependent upon theta. Theta is a position of the rotor. So, in that case I can be taken out of the derivative because it is not a function of theta. So, we can take it out. So, we can say that it is half I square into dl by d theta. So, what we understand that the torque in a switched reluctance motor is proportional to I square, and also it is proportional to dl by d theta. So, it means there has to be an inductance variation with respect to the position, that is theta, and this is the principle of switched reluctance motor. Now, let us take an example of a 8-pole stator and 6-pole rotor switched reluctance motor. This is also known as SRM. The short form of switched reluctance motor is called SRM. So, we will be taking an example of an SRM with 8 stator poles and 6 rotor poles. Now, if we want to see the constructional feature, we will have an idea how this works. So, let us draw this motor. This is a stator. We have 8 poles. So, let us try to draw the poles here. So, 8 poles means they have to be shifted by 360 by 8, that is 45 degree. So, 8 pole. So, the stator pole pitch is equal to 360 by 8, that is equal to 45 degrees. So, we can draw the stator poles here. These are the poles of the stator, one pole, second pole, third, fourth, fifth pole, sixth, seventh, and eighth pole. So, the stator has got 8 pole structure. So, we can now complete the stator structure here. the poles are basically projecting in nature. They will project out the stator periphery. We can now complete. Now, let us come to the rotor. The rotor has got 6 poles. 6 poles means the pole pitch is 360 by 6. So, rotor pole pitch here is equal to 360 by 6, that is equal to 60 degrees. So, let us try to draw the rotor poles. The rotor will have a structure here, and here we have to have 6 pole structure. So, we can have the rotor poles like this. This is one pole, second pole, third pole, fourth pole, fifth pole, sixth pole. So, these are the rotor poles. So, we can now complete the structure of the rotor. Rotor does not have any winding. Rotor has got only slotted structure like pole and slot, pole and slot that we are drawing here. Now, this is a pole, we have a slot here, then again we have pole and then slot, pole and slot. So, this is the structure of the rotor. The stator also has saliency, rotor also has saliency. The stator is slotted, rotor is also slotted. But the difference between the stator and the rotor is this: the stator will carry concentric windings, rotor does not carry any winding. So, in the stator we will have winding. Say we can have the windings here, these are the stator windings. This is also another winding here. We have windings in this case. The stators, poles, they have concentric windings. So, the stator carries windings. So, we can call this as, suppose this is phase A, we can call this to be A prime, it is diagonally opposite. Similarly, if we say this is B, the diagonal opposite is this, we can say B prime, and if we say this is C, this could be C prime, this is D and this could be D prime. So, in this case we can say that we have 4 phases and the phases are A, B, C and D. Although we have 8 pole structure, we have 4 phases and each phase has got 2 windings, A and A prime, B and B prime, C and C prime and D and D prime. So, this is the structure of the stator. The rotor, however, does not have any winding, it is a slotted structure and that is why it is lightweight. The rotor does not have any winding, does not even carry any bars, unlike a squirrel cage induction machine where the rotor has got aluminum or copper bars. Here the rotor even does not have any bars. So, the rotor weight is also very small. So, the total weight of the machine is small compared to an equivalent induction machine, and that is why this is specifically meant for those applications where we need lightweight motors. However, the control is little difficult here. Now, as you have already seen that the torque is produced by the variation of inductance I square dl by d theta. and if I square is present only at dl by d theta which is positive, then only we will have positive torque production. So, here we see that the rotor rotates, as the rotor rotates. So, we will be, say for example, if the rotor rotates like this in the anticlockwise direction, the inductance of every phase will be changing. If we concentrate on phase A, now phase A pole is facing the tooth of the rotor. We have the rotor here and this is the stator. So, the inductance of every phase is a function of theta. As it moves, it basically moves by an angle theta. So, we can draw the variation of inductance of every winding with respect to theta. In fact, we have 4 phases here, phase A, phase B, phase C and phase D. If we plot for any one phase, suppose phase A, the same thing will be happening to phase B after some delay. So, what we will do, we will be plotting the inductance variation of any given phase as the rotor rotates. So, we have another specification. Stator pole pitch is 45 degree and rotor pole pitch is 60 degree. And we have also been given that pole is to pole pitch is equal to 0.4. In fact, we can say pole is something similar to tooth. Tooth is to tooth pitch is equal to 0.4. Same thing, because the poles are something similar to tooth. The rotor will have some teeth, the stator will also have some teeth. So, we can use tooth for pole. A pole is something similar to a tooth and pole pitch is equivalent to or similar to a tooth pitch. It means this is the pole, the stator will have this pole structure. So, if this is the pole, we have got tooth here and this is the slot. So, this is the tooth pitch. So, tooth by tooth pitch is equal to 0.4. So, let us see in this case that let us try to see the stator tooth pitch. Stator will have 8 tooth or 8 poles, that is 360 degree by 8, that is 45 degrees. What is the rotor tooth size? So, tooth is 45 into 0.4 is equal to 18 degrees, and this is also same as pole. So, the rotor pole will occupy an angle of 18 degrees. So, it means this is the rotor pole, and if we linearly develop this, this angle is 18 degrees. And the stator tooth, the stator tooth pitch is here 45 degrees, which includes the tooth and the slot. So, this is 18, the tooth is 18 and tooth plus slot is 45 degrees. So, what is the slot here? Stator tooth. So, this is the stator tooth. Similarly, we can have stator slot, stator slot. The stator slot is 45 is the tooth pitch minus the stator tooth is 18 degrees. So, what remains is the stator slot angle, and this angle is 45 minus 18, and that comes out to be 27 degrees. So, this is 18 and what remains here is 27. This is the stator. Similarly, for rotor has got 8 teeth. Rotor has got 6 teeth. So, the rotor tooth pitch is 360 by 6. So, we can say that the rotor tooth pitch is 360 by 6, that is equal to 60 degrees, and the rotor is like this facing the stator. So, this is the complete 60 degree, which includes the tooth plus the slot. Now, what is the rotor tooth pitch? We can say that the rotor tooth pitch, rotor tooth here is 60 into 0.4, that is equal to 24 degrees. That is the rotor tooth. What about the rotor slot? The rotor slot is 60 minus 24, that is equal to 36. So, in fact, this is the rotor tooth, and the rotor tooth is 24 degrees, and the rotor slot is here, this is 36 degrees. So, 36 is the rotor slot, 24 is the rotor tooth, 36 plus 24 is 60, that is the rotor tooth pitch. We have been discussing about the Swiss reluctance motor, the rotor and the stator configuration. Rotor tooth pitch is 60 degree, and out of 60 degree 24 is the rotor tooth and 36 is the rotor slot. Similarly, the stator tooth pitch is 45 degree, and out of that 18 degree is the stator tooth and 27 degree is the stator slot. Now, let us develop the, actually the motor is a cylindrical structure. So, if we take a cross section, the cross section will be a circle, and the cross section we have already seen here, that we have the stator and we have the rotor. The stator carries winding and the rotor does not carry any winding, and when the rotor moves, every phase of the stator will see alternately the pole, the rotor tooth and the rotor slot, the rotor tooth and the rotor slot. Thus, the inductance of every phase will undergo variation. So, if the inductance of every phase will undergo the variation, to find out the torque, we should be able to find out the variation of inductance with rotor position. Although it is a circular structure as we are seeing here, we can develop this linearly. So, what we will do, we will cut it and develop this linearly, and we have the information about the various angles, the stator tooth pitch, the stator tooth and the slot individually, the rotor tooth pitch, the rotor tooth and the slot individually. So, we will be developing this in a linear fashion. We will cut it and open it, and this will look like this. So, we have the stator, and the stator slot is 27, and then the tooth is 24. Again we have the slot and then the tooth. So, this is the stator. We are concentrating on one phase. We have the windings here. We are interested to find out the inductance of this winding. What about the rotor? The rotor is below the stator, and here the stator, this angle is 27 degrees. The slot angle and the pole angle or the tooth angle is 18 degrees. The rotor, we will start our reference from this position. The rotor is just waiting to go under the stator pole. The rotor tooth is here and tooth here is 24 degrees. So, this will occupy up to this position. This is 24. this angle is 24 degrees, and then the rotor slot is 36 degrees. So, we will have here the rotor slot, this is 18, and then we have another 18 here, and this makes 36. And then again we have a slot, in this case the slot is 24, and this will continue. So, this is the rotor structure. So, the stator is stationary, rotor is moving, and the rotor is moving in this direction towards the right with a speed, and angle is theta. Theta is basically measured from this particular position. We can say this position is theta. Now, at the starting theta is 0, and the rotor is just waiting to come under the stator. Now, we can plot the inductance of the winding on the stator. Say for example, we can call this winding to be the phase A winding, A phase. So, let us try to see how the phase A inductance vary as the rotor comes under the stator and moves away. So, we are now plotting the inductance of phase A. We have theta here in the x axis, the inductance L in the y axis, and at this position we can see that the stator is seeing a larger air gap. So, this air gap is quite large, this air gap. This is the air gap, that is Lg. So, gradually the rotor will move under the stator. So, after some time the rotor will go under the stator. So, this will be somewhere here, and this particular portion will go somewhere here, because this is moving in the right side. So, the stator will see a decrease inductance. So, the inductance decrease air gap, the inductance of phase A will gradually increase. So, initially theta was equal to 0. So, this is L minimum. We have some minimum inductance, that is L min, and as the rotor moves, the inductance of phase A will increase, because the rotor tooth will be coming gradually under the stator pole, and the inductance of that particular phase will increase. How far will it increase? It will increase after the rotor completely comes under the stator. So, it will take 18 degrees for this to increase from 0 to some L maximum. Here we have L maximum. Initially it was L minimum, and then we have some L maximum here. So, it will take 18 degrees to go from L minimum to L maximum. So, this is 18 degrees, and then this rotor has already come under the stator. It will stay and it will again move away, and for some time there will be overlap. The air gap will not change, the air gap between the stator and the rotor will not change, that will remain constant, and then that is called the overlap region, and the overlap will be for again for 6 degrees. So, the overlap will be here, the inductance will be constant for 6 degrees, because this is moving away and this comes fully under the rotor. So, it is something like this, and then this is still moving away. So, this overlap will be for 6 degrees, and 6 degrees plus 18 degrees will be 24 degrees. So, up to 24, from 18 to 24, the inductance of that particular phase will in fact be constant, and after that the rotor will be moving away further, and again the inductance of phase A will decrease. So, if this further moves away, this inductance will further decrease, will be in the same way like this, linearly it will decrease in fact, and this will again take 18 degrees to come to L minimum. This is 18 degrees, 28 plus 18 is 42 degrees. So, this is how the inductance varies. It goes from a minimum value to a maximum value linearly. We are in fact neglecting the fringing effect. It goes from minimum to maximum, then stay for some time at the maximum value, again it goes to the minimum value, and at that minimum value it will again stay for some time. So, at the minimum value it will stay for, this angle is in fact 36 degrees. It will stay in this minimum value for again 18 degrees. So, this is 36 and 42 plus 18 is 60, and the same thing will again repeat, inductance rising, then remaining constant, then decreasing, and then remaining constant again. So, this is how the inductance of a particular phase changes. So, if we plot dl by d theta, this inductance variation is against theta. Theta is in the x axis, and this is how the phase inductance will change, and this will happen for phase B and phase C also after some time. So, dl by d theta, which is important for the torque production, because we know that the torque is equal to I square dl by d theta. So, this is the expression for the torque. So, this dl by d theta is extremely important. So, we need to evaluate what is dl by d theta. So, dl by d theta is the derivative of the inductance with respect to position, that is theta. So, we can differentiate that and find out what is dl by d theta. So, here what we do here, this is inductance, and here we can calculate what is dl by d theta. So, here it is rising. So, we can say that the derivative is constant. So, it is positive, the derivative is positive here. Then from 18 to 24 it is again constant, inductance value is constant, and hence the derivative will be 0. And from 24 to 42 the inductance is decreasing, and hence the derivative is negative. So, we will have minus dl by d theta. So, this is positive, 0 and negative, and from 42 to 60 inductance is again constant. So, dl by d theta will be 0, the derivative of the inductance will be 0. So, the inductance variation with respect to theta and dl by d theta will look in the following fashion. So, this is dl by d theta, and this is responsible for the torque production. If the inductance is not a function of theta or it is almost constant, then torque is 0. So, if dl by d theta is 0, torque is 0. So, it is because dl by d theta is finite, that is why when we inject current there is a torque production. So, how will the current be injected? We have both dl by d theta positive, dl by d theta negative. Current is injected in such a fashion, it exists only during the positive dl by d theta, because we want positive torque. So, in fact, the current should exist, if we are switching the current should be allowed to exist in the positive dl by d theta and should be 0 for the negative. This is what is the current for the positive torque. So, the current should be confined to the positive dl by d theta region to produce a positive torque. Now, this is achieved by applying a voltage at the suitable time. Now, we will see how a voltage is applied. So, we have this phase here. This is, say for example, the stator phase A, and this inductance is L and the resistance is R. So, we have a switch in this case, we can have a switch here, and let us say we apply a voltage to this particular phase. We may have a freewheeling diode in this case. So, if we have arrangement like this, we can apply a voltage that is VDC. So, if we apply a voltage called VDC, when we apply this particular voltage, what happens here is that the current flows through the winding I. So, we can write down this equation that V is equal to the resistance drop plus N d phi by dt. phi is the flux linkage in the winding. So, V is equal to Ri plus N d phi by dt, and here we want to find out what is phi. So, phi can be evaluated like this, and that is say it is equal to VDC, that is a constant voltage. So, if we want to find out what is phi, we can say that V is approximately equal to N d phi by dt, neglecting, we make some simplification, neglecting the resistance drop. The resistance drop is usually small compared to the induced EMF. So, if the winding is made up of copper, the resistance is very small. So, we can ignore the resistance drop compared to the induced EMF, that is N d phi by dt. So, if we do that, we can say that V is approximately equal to N d phi by dt, that is equal to VDC, and we need to find out what is phi. So, phi here is equal to VDC by N into dt integral of that, and that is equal to integral of VDC by N into omega. Omega is the rotor speed. So, we can add or multiply this omega in the denominator, also in the numerator. So, we have d omega t, and that is equal to integral of VDC by N omega into d theta. Now, usually for a steady state condition, the speed is constant. So, if the speed is constant and VDC is also constant, we can have a simple integration that phi is equal to VDC by N omega integral of d theta, and that is equal to VDC by N omega into theta. So, in fact, here what we find that if we apply a voltage, the flux will rise linearly with theta. The flux phi is proportional to theta. So, what we do here, we have this inductance, and the inductance is a function of theta, and it varies like this, rising, then remaining constant, then again falling, then remaining constant, then rising and remaining constant in this particular way, and before that also it was constant. So, this is 0 position, and what we do here, we apply the voltage in a suitable fashion, so that the flux linkage is followed, will change in the following fashion. This is the flux linkage phi. This is the applied voltage V. V is, in this case, we apply here plus VDC, and then for this zone we apply a negative voltage, so that the flux dies down to 0. So, this is the applied voltage, this is the flux linkage, and this is the inductance. So, as we apply the voltage, the flux will change linearly. We have applied a voltage here little earlier to that. So, when we apply the voltage with some advance angle, the flux will linearly rise, as we have seen already, flux equal to VDC by N phi into theta. So, in fact, phi is proportional to theta. So, it changes linearly, and after some time we apply negative voltage. So, we apply a negative voltage, the flux is brought down here. So, this is plus VDC and this is minus VDC. So, in the next lecture we will be discussing how to control this Swiss reluctance motor and how we can have variable torque and variable speed operation with a Swiss reluctance motor.